Okay, so last time we left off on Michaelis-Menten model, which is going to explain many of the observations of enzyme kinetics in a model format, which is nice because that means you have theoretical pinnings to help you, right? So here we have the proposed Michaelis-Menten model, which is an enzyme adds to a substrate. They're going to then bind to form the complex, right? And then what's going to happen with the enzyme substrate complex is if it goes forward in the reaction, which there's always a chance it won't, right? It will actually produce product, which is then released, okay? And so this is then the enzyme plus product being released, and that's our product sides of the reaction. Okay, so notice, by the way, that it's joined as two equilibria. Each of those equilibria have energetic relationships, including kinetics, right? And so we have a rate constant 1, which is for the first step of the equilibrium for this Michaelis-Menten model. And then the reverse of that reaction, which would be the enzyme substrate falling apart, is going to be K negative 1, right? Reverse 1, okay? The second one, K2, is going to be forming the product. And if we go the reverse direction, which would be the product binding to the enzyme and going back to substrate, that's going to be K minus 2, right? Remember that in all enzymes, all the time, this reaction goes back and forth, right? Okay. Okay, does anybody have any problems with that so far?
So it goes like the enzyme binding to the substrate, and then...
Yep. Then you have to do that. Once you do that, you can then convert it to product and release it. Okay? Now, in this form right here, the complex ES, this would be a minima within the transition state. Remember those intermediates? So I know it says ES, but actually that S is more like part of the way to P. Okay? Okay, so at V0, again, that's that 0 time velocity, that linear portion of our velocities, right? Where we don't have any product made yet. There's going to be negligible product formation, and so there won't be any back reaction. So for when we do the V0s, and this is why all the homeworks and stuff had V0s, is because this K minus 2 reaction, that rate there for that backwards reaction, doesn't exist, okay? It's 0. You don't have any backwards reaction because you have no product. Okay? Yeah. And so we can then simplify this, and this gives us our actual Michaelis-Menten model, which we're going to use, the part that we're going to use, which is 7 here. And notice the backward reaction is gone, our K minus 2 is gone. Okay? So we have now simplified this reaction, because we're always going to be looking at time 0, right? Where we have no product. Okay, so this right here is again the Michaelis-Menten kinetics. That's the results of our Michaelis-Menten model. So what we can see is the reaction velocity. If we plot the reaction velocities as V0s, initial velocities, right? Remember, we always work in initial velocities if we're talking Michaelis-Menten, okay? Or most times in enzymes, to be honest. We're always going to get the V0 plotted against the substrate concentration. What would you expect for that velocity of the reaction versus substrate concentration? As we increase substrate, velocity goes up, right? Now keep in mind that we have a maxima we can reach, right? And we can never go past. This means it always has to be a logarithmic relationship, right? We have to approach the maxima but never reach it. And you can see it approaches this V max but never reaches it. What would be V max, by the way? Exactly. We've maxed out this right here, right? We have bound all of our enzyme essentially. We can't actually do that, but we've come as close as we can. Okay. And so if we go 1/2 of V max, what does that tell us? After the active sites are binding, or another way of saying that is that the amount of free, the amount bound, yes, the amount free is equal to the amount bound, right? And so this means that our normal K values, our normal equilibrium expressions, we're going to cancel those terms out, aren't we? The free and bound, because they're going to be equal. And this means that we cancel everything out and we end up with Km would be whatever substrate concentration is down here for 1/2 of Vmax. Okay? So if we take Vmax, find half of that Vmax, draw it out to our line, draw it down to the substrate and find which substrate that corresponds to, that's Km. Okay? And that's all because all of our terms with the receptor, which is the one that'll be in your homework, the R receptor, but in this case, enzyme, right? Those will be equal, right? Our free enzyme and ES, and they'll cancel, leaving behind substrate only. Okay, this is actually what this looks like. So the catalysis results from the ES complex is slow relative to the rate of formation of our ES complex. Typically what happens is the ES complex is very fast, and it takes a lot more energy to go ahead and do the reaction. Okay? The overall energy as an activation energy. In case that wasn't clear. The overall reaction rate can then be expressed as this right here. And so V0 equals K2 ES. If we look at that, that's that part of that reaction right there, right? Because we just mentioned that this is typically very fast. This is the rate-dependent step in basically every enzyme substrate reaction, according to the Michaelis-Menten theory. Model, I should say, excuse me, which is backed up by the theory. The rate of formation and breakdown of ES are going to be given by these terms right here. So the rate of formation of ES would be given by this term. Note that's just the rate equation. Okay? So we have K1, which is the forward for the enzyme substrate complex forming, and the reactants, right? ES, second order overall. Okay? The rate of breakdown of ES would be this form right here. Note that ES can break down two different directions, right? It can go backwards to freeing the substrate and freeing the enzyme. Okay? It can go forwards to making product, right? And either way, we would have the enzyme substrate complex, but we have to account for those two, and so our constants will be added. Another way of saying this is we would have had two rate laws. We've added those together, and then we've taken ES from both of them and put it into one term. You know, you can do that. If you redistribute this would be K minus 1 ES, and then, yeah. Okay. I just taught general chemistry, so I'll try to not remember that you guys have had that math. You don't need it. So to simplify again, we need to use the steady state assumption that the rate of formation of ES is going to be equal to the rate of breakdown of ES. And so you would have these two terms equal. You'd set them equal to each other. We can then rearrange that equation to get all the K terms on one side. Because what are big Ks? It's an equilibrium constant, but why is it a big K? It's made of little Ks. Yep. Yeah, you guys kind of remember. Yeah, that's something I say a lot, right? Because it's true, okay? And so if we gather these together by taking these two equations, solving for ES over E times S over ES over here, and then dividing this over here, we get this term. Anybody want to try to guess what that term is? The Michaelis constant, because we're doing the Michaelis model. Damn biologists. Okay, so again, this is a new constant. This is the Michaelis constant. It's going to have units of concentration because you'll have these terms canceling each other out with their units of seconds and molarities, typically. This is independent of enzyme and substrate concentrations because it's composed of the constants, right? It doesn't have any of the concentrations within it, okay? Or another way of saying that is it's just like any other equilibrium constant, that it will tell you the ratios of product and reactant, right? Not the amount of each. So if we insert these into equation 13, into equation 12, and solve for ES, we can actually get this value right here. And this is why we've made this new equilibrium constant, okay? Is we can have ES, which is the enzyme substrate complex, equals the individuals, E and S, divided by Km, okay? Okay, by the way, again, that is an equilibrium constant. You will note that is the equilibrium constant for this relationship right here. That relationship is kind of a reverse. It's almost like a reverse equilibrium constant, okay? And the reason for that is the one you're most concerned with in this relationship is the enzyme substrate complex. That's the one you're really looking out for, all right? And so that is actually in the denominator, okay? Your enzyme substrate will then be in the numerator, right? Notice it's normally products of reactants, isn't it? So we're looking at this in reverse, aren't we? I.e., if this was a normal equilibrium, we're looking at this as if it's coming apart. The enzyme substrate is coming apart, okay? You'll note that this is, because of how we arrange this Michaelis-Menten at first, it makes it a little bit confusing. But if you think about it in terms of like a KD, dissociation constant, it makes a lot more sense. The normal way to do a dissociation coming apart is from the complex being formed, right? And so Km is the complex is formed coming apart, okay? Okay, so this right here is that relationship. The concentration of free enzyme is going to be equal to the total enzyme concentration, which would be ET, of course, minus the concentration of our enzyme substrate complex, which gives us this equation. That's true for any sort of relationship like this, right? Your total is your different components you can have, okay? You only have two different components with enzyme in it. If we insert that into the previous equation, we can get one that's even easier to deal with experimentally. And so we actually get ES, the enzyme substrate complex, equals the enzyme total, which is what you probably put in there, right? Minus the enzyme substrate times the substrate concentration, which will, again, you can set up conditions where you can assume that to be what you put in, right? Over the Km. You can then rearrange this to further simplify it. There's two major ways that you can rearrange this, but there's many, many ways that you can actually look at this equation and use it in various different ways. But here is a couple of them. So this would be the ES, and then we have rearranged these right here. See that? We've taken terms out. Alternatively, you can rearrange it like this. If we then take this and substitute this expression for ES into equation 8, if you go all the way back to 8, you'll see that. We get this relationship right here. Okay? Notice that we've actually now got it down to V0. Okay? And this then has the K value, K2, enzyme total, substrate divided by substrate plus Km. Okay? All right, so the maximal rate, Vmax, is actually going to be obtained when we would have the enzyme substrate complex would be all of our enzyme total, right? Or essentially so, right? Most of the way to it. Okay, and what that means is that at Vmax, it's going to equal K2 times the E total. So if we substitute equation 16 into equation 15, which is the one we just got here, we'll actually get this one right here, which is the Michaelis-Menten equation, okay? And that's where that came from. Note, by the way, now we have it almost all experimental values. So we have V0, which is that initial rate, right? Which we can measure experimentally. That's going to equal Vmax. We can measure that experimentally as well, can't we? All we do is put so damn much substrate, we blow out everything else out, right? Or another way of saying that is when we get enough substrate, we'll eventually hit Vmax several times, right? And then we have the amount of substrate we put in right there, don't we? Okay? Most cases, the amount of enzyme is going to be insignificant versus the amount of substrate, right? Because we can put a lot more substrate than we can enzyme. And so we basically can always assume that whatever amount of substrate we put in, that's it right there. Okay? And then we have Km, and that's the one you typically would find experimentally. How would you find it? You'd find V max and do 1/2, right? Okay? Remember to trace down to the substrate. Don't take half of V max as your Km, okay? That makes sense? All right. Be very careful about that. It's a very common mistake. Okay, so again, this Michaelis-Menten equation is going to describe your initial reaction velocity as a function of your substrate concentration and not much else. The rest of this stuff's constants. Okay? So when the substrate concentration equals Km, then you would actually have V0 equaling 1/2 of Vmax. The Km is actually the substrate, of course, at half of the maximal value. Right here we have some different variations in Km that can have physiological consequences. So here we have alcohol dehydrogenase. This converts ethanol into acetaldehyde. If you ever go out for a night of drinking, college students and all, you have experienced this one. Okay? Okay, so the aldehyde dehydrogenase converts the acetaldehyde to acetate. Most people have a low and high Km form of aldehyde dehydrogenase. In persons that are sensitive to alcohol, the acetaldehyde is processed only by the high Km form. And so what you get is excess acetaldehyde will escape into the blood. And this is actually what creates all those physiological effects where you get the hangovers and everything else. Okay, this is what creates the damage from a night of drinking, right? So again, the Michaelis-Menten equation then can be transformed into one that yields a straight line plot. So we look at the previous equation we looked at. We can actually subdivide the different terms out, rearrange them, and get a linear plot out of that. This would be a Lineweaver-Burke plot, by the way, which is a double reciprocal plot. It's going to be a plot of 1 over V, so 1 over V0 equals, this is the slope right here, which is Km over V max, right? This will be then times 1 over S. This is your X value. Don't forget when you do these, your Y values are 1 over V0, right? Don't put in V0 because you'll get the reciprocals. This will then be plus 1 over V max. What's your Y-intercept? One over V max. Yeah. Okay. Here we go. Okay. So right here is the Lineweaver-Burke plot. And so what you can see is once we plot these out, we get this Lineweaver-Burke plot. Now, a Lineweaver-Burke plot is a little bit unique because normally we just stop at x equals 0 and we don't look at anything else, right? In almost every relationship we've ever had, okay? It's very unusual to look at the x-intercept, right? In the case of a Lineweaver-Burke plot, actually your x-intercept is incredibly important. It makes using this easier, okay? You don't need it, but it makes your life easier. So the y-intercept is 1 over V max, right? If you want V max, you just take 1 divided by the value you'll get V max, right? If you want Km, you can actually take negative 1 over the value you get from the x-intercept, okay? If you can't figure that out for whatever reason, because they didn't plot it, you can't plot it, you can't figure out how to get x-intercept, whatever, okay? You can also get it from this over here. So if you have the y-intercept, you get V max, right? You multiply the slope, you can get the Km. Okay? Okay. All right. Did anybody have any questions about the Lineweaver-Burke plot? Okay. Okay. Now keep in mind, if you have a very high Km, what does that mean? Where was it? Yeah, so this would be Km, right? So a high value of Km means that you disassociate a lot. You don't bind very well and you don't go on to product very well. Okay? A lower Km actually means you form a lot of the complex, right? Yeah. So it's a little bit, I know you're thinking like enzymes, right? And this would be an equilibrium constant for the enzyme. But it's actually closer to a dissociation constant. Okay? Not a reaction equilibrium constant.
So a high Km means you have more.
Enzyme substrate. Separately. A low Km small value is going to mean you have a lot more of the enzyme substrate as together complex, which you have to go through to get product. Okay?
So ES would be the concentration of the enzyme bound into the substrate.
It would. Yep. So that's down here. I know, because of how we first start with the theorem, with the model, that equilibrium, the two equilibriums together, really kind of tricks students. Very, 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 very tricky at first. So Km is approximately equal to S in vivo. This allows the enzyme to display elasticity or sensitivity to changes in your substrate concentration. Essentially, we're typically in an equilibrium-like state. We would then be in the normal sort of buffer regions. Okay? Km approximates the dissociation constant, Kd, of the ES complex, but this only really happens if the K negative one is much, much greater than K2. Okay? Which we can sort of assume, and we have made assumptions to be able to do some of this math, but in vivo, that may not be true. Okay? In an artificially set up situation where we just max out the substrate and kill it, and we look at just as we're putting stuff together, we can set those situations up. But in real life, in your body, this is not true as much as you might want. This is actually not true that often. So if the K negative 1 is much, much greater than K2, what we see is the Km would actually equal the reverse K negative 1, which is the substrate coming off and freeing, over the K1, which is the one where we form the complex, right? And so we could actually simplify this to these terms. So KES would equal this same value here, which equals, in this case, just the K negative 1 over K1. Remember, this is different than what we had just discussed, which is where it has the K2 up here. Okay? So what we're discussing now is that this value here, if this is much, much smaller, then adding that value doesn't do anything, right? And so we can assume that that is not important and get rid of it. Okay? Okay. All right, so these Km values of some of the different enzymes, and so here we see some of the different Km values. Everybody see that okay? Okay. Remember that when we're talking about Km values, those will be unique for the substrate you're binding. If you were to do like an analog that binds better, you would have a different K value, right? So you'd have a different Kn. So K2 times Kcat, cat being the catalyst one, the turnover of the number of the enzyme, which is the number of substrate molecules that can be converted into product per second. This is how fast it can do the reaction in going forward. Okay? Vmax is going to reveal the turnover number. E total is known. So if we have E total, if we can figure that out, we know how much enzyme is in our system, we can actually get the amount, the rate of our catalyzed reaction. And that would actually just be Vmax. Another way of thinking of this is if you want to know how fast you can get a turnover on something, like how fast an engine can go, what do? You max it out, right? Pedal to the floor, maxed. Well, that's all the way binded, right? We have maximized it out, okay? Same thing happens for Vmax. So if you maximize Vmax, and this K value right here is not going to have anything to do with the binding, is it? Okay, because we bound everything. The K value in this case, if we're on Vmax, is just purely going to be the forward of the reaction with the catalyst, right? Okay. This does actually assume that the catalyst greatly enhances the reactivity, which it should, but if it isn't a large enough enhancement, you could actually get some error in here, okay? All right, so if we rearrange that, by the way, we can actually see that Kcat equals Vmax over the enzyme total. These values then are ones that we can experimentally determine by setting up in a reaction with our catalyst or enzyme properly. And then we can figure out what a Kcat for that enzyme would be. Okay? So here is Km and Vmax. This is going to permit the formation of FES. This is the fraction of active sites that are filled. F meaning fraction, ES meaning enzyme substrate complex, i.e. active site is filled, right? This is actually going to be FES times the V0 over Vmax equals substrate divided by substrate plus Km. This actually makes a lot of sense if you start thinking about this, because this value right here just directly corresponds to that. Okay? That's actually a ratio of the enzyme being bound anyways. So the turnover numbers of some of the enzymes are right here. These are how many times it would produce product per second. Notice our carbonic anhydrase has a 600,000 turnover, which is pretty massive, right? Okay. Whereas our lysozyme has a much, much smaller one. DNA polymerase 1 only has a 15 turnover per second, which is still pretty fast if you think about it. But, yeah. Faster than your eyes. Your eyes have a turnover of 5 per second, if you're curious. So under physiological conditions, the concentration of substrate over Km ratio is typically going to be between 0.01 and 1. So when S, the substrate concentration, equals Km, the enzymatic rate is going to be much less than the Kcat. This is going to be because most of your reactive sites are unoccupied, and so you're not maxing out the amount of substrate your enzyme can convert to product at any given time, right? Okay, and so in that case, the V0 is going to equal the Kcat over the Km times the enzyme times the substrate. So when the substrate is much, much less than the Km, your E is approximately going to be equal to your E total. Okay, again, substrate is much, much less than Km. You have very low concentrations of substrate. So the majority of your enzyme is going to be on the unbound form, right? Okay. Yes, because we have very little substrate right now. We have setup conditions, so we have almost no substrate, and we have a lot more enzyme going on. Okay? Okay. Though it's not as quite straightforward as that, keep in mind it's actually the substrate is much, much less than the Km. Okay? Meaning the majority of your sites are not bound. Okay, so this right here is V0 then is going to equal the Kcat over the Km times the substrate times the enzyme total. Notice all that's happened is instead of having the enzyme that we have to figure out how much enzyme is free, here we have enzyme total, which we could have started with a total amount of enzyme, right? So specificity constant. This is actually Kcat divided by Km. That's going to be your rate constant. We refer to this rate constant of Kcat divided by Km as the specificity constant. The reason we do that is actually if we expand these terms, we can actually see the math behind it. So we take the Kcat divided by Km. What you would see is that is actually going to be this right here, Kcat times K1 over K negative 1 plus Kcat. This is going to equal then the Kcat divided by K negative 1 plus Kcat times that entire term, K1. Notice we've just extracted that out. This is going to be less than K1. Notice that this is going to be a proportion of K1. Because Kcat is on the top and bottom, the lower part is always larger than Kcat. Can you see that okay? See that okay? This is always a fraction of K1. Okay. Thus the specificity constant. All right. Again, the Kcat over Km is always less than K1. Again, that's because the rate of formation of our enzyme substrate complex is always limited by the diffusion controlled encounter of our ES. So we cannot form all of our ES as fast as we can possibly do it, right? They have to come together, okay? And so it's always lower. Some of the enzymes are going to have obtained kinetic perfection. They would have a Kcat that's divided by Km rates that will approach the rate of diffusion. And that would be the top performers, very small proportion of the enzymes, okay? They're the ones that diffusion just brought it straight through the damn enzyme. Congratulations, that was amazing. But obviously not the majority of cases, right? The vast minority of cases, typically. This right here is the amino acid in an ester. This is the amino acid side chains in these. This would then be the Kcat divided by Km. That would be your units, by the way, in case you're curious. And what we can see is that these amino acids in the esters are of different Kcat, Km values right there. And again, the enzymes with the Kcat over Km that are near the diffusion controlled limit are these ones right here. This is how fast these can happen according to diffusion. Okay? So most reactions in biological systems are going to be bi-substrate reactions, meaning two substrates have to bind and react, right? Okay. So multiple substrate reactions can be divided into two classes. These are going to be sequential reactions. What do you think sequential means? Yeah, one after the other, got it. And then double displacement reactions. We have to double displace. So in sequential reactions, again, all substrates have to bind to an enzyme before any product is released. So you have to bind one, bind the other, then you can get product. Okay. These reactions may be ordered or random. So it could require one substrate to bind, substrate 1, then substrate 2 combined, then you get product. Or it could be I bind whichever one comes first. Substrate 2, substrate 1, I don't care. And then I bind the other one, I get product. Okay? So in ordered sequential mechanisms, the substrate bind the enzyme in a defined sequence. In random sequential mechanisms, the order of the addition of substrates and the release of the products is arbitrary and can happen in any specific order. This right here is an ordered sequential reaction right here. So what we see here is the enzyme takes on the NADH, then the pyruvate. These are the two things it needs. It then can complete the reaction by converting the pyruvate to lactate, which it then releases. Then it releases the NAD+. And then we end up with free enzyme again. Okay? Is that obvious how to read it? Anybody have any problems with how to read this? No? Okay. Fantastic. Fantastic. It's like somebody taught you organic chemistry. Maybe. Okay, so this is a random sequential reaction. Random sequential reactions look confusing. when you look at the diagrams, because they have to account for the fact that they're random, right? That you can happen in any order. And so what we get here is the enzyme can take on either the ATP or creatine first. Doesn't matter, okay? And so some of them take on ATP, some of them take on creatine. Doesn't matter. Once it takes on ATP, it then will take on the creatine at some point. It will then do the reaction, and then it will release one of them first, the second one second. Okay? Doesn't matter. Theoretically, you could get cases where it releases both of them at the same time, but that's incredibly unlikely. Okay? Because again, your random chance, the likelihood of both of those falling that release at the same time is very minimal. Your double displacement reactions, another way of saying this is ping pong reactions. Everybody say it with me. Ping pong reaction. You got to say something ridiculous in biochemistry. Congratulations. That's a great naming, right? But ping pong reaction, and it literally is like a ping pong, right? You bounce it back and forth. So one or more of the products is going to be released before all substrates bind the enzyme. And so what you'll get is you'll get one taking on a substrate, you'll get a product released, and then you'll take on another substrate. Not the same one, the other substrate. Okay? And it's like ping pong, right? You play with A, you play with B. You play with A, you play with B. And you keep volleying it back and forth, right? Yeah. This is going to be characterized by the formation of an enzyme intermediate. This is the example of it right here. So here we have the enzyme. It takes on aspartate, so we get the enzyme aspartate complex. It forms oxaloacetate, and it releases that. It then is going to have a modified enzyme. Notice that. It is not E anymore, is it? See that? That is not E anymore. That is an enzyme complex with a amine. See that? An NH3 attached to it. We did not regenerate our free enzyme, did we? Okay? So we have taken on an amine. We then will bind with alpha-ketoglutarate. We will do the reaction, creating glutamate, and that will finally release our free enzyme. And so if you look at this on the top, it is like a ping pong, right? Okay? Serve, receive. Received. Received to the other person. Okay? Okay, does anybody have any questions about that? By the way, what do you think you add to the glutamate? Some sort of amine group, right? Yeah. So that's transferring that functional group, isn't it? Okay, so this is allosteric enzymes. So the allosteric enzyme is often not going to obey Michaelis-Menten kinetics because that allosteric interaction is going to change the binding, isn't it? Okay? So the allosteric enzymes are often going to display sigmoidal plots. This is a sigmoidal plot. So yeah, it looks like an S shape. Okay? Usually irregular sigmoidal plots, not perfectly symmetric ones. So again, this would be that same Michaelis-Menten sort of graphing that we would have done before. Before it had been a nice, beautiful logarithmic relationship with a Vmax up here, right? Okay. Now we are sigmoidal. You can still see there's going to be a Vmax eventually, but we have modified that Michaelis-Menten plot because of our allosteric interaction. So the rates of enzyme catalyzed reactions are going to increase as temperature increases. This is true for all reactions. As we increase temperature, what usually happens? The rate of reaction increases, right? If we increase the temperature, what happens to our cooking speed? Cooks faster, right? Okay. However, there is a problem. Proteins can be denatured. What are holding proteins together? Hydrogen bonds and nonpolar interactions, right? Okay. What happens when you start heating those things up? They start melting, don't they? You start breaking them. And so what's going to happen is our enzyme activity will increase up to a point. And once we reach that temperature, it will drop off very rapidly. Okay? And we will denature our protein once we get into this area. Okay. By the way, this point right here, see how it like has a little bit of time here, a little bit of temperature, where there's a little bit of like, it's still reacting pretty good, but it's stopped going up. This is partially denatured. It's not so denatured that it's causing a problem with the binding, but it's denatured enough that it's starting to come apart. Okay? Okay, so let's talk about a bit about the coloration of Siamese cats, because why not? This can be explained by, again, the variation in your enzyme sensitivity due to temperature. So here we see the tyrosine. This is tyrosinase. This will convert us to this form right here. Tyrosinase can also convert it to this right here. Eventually, that goes on to melanin. Okay, melanin being the coloring in most animals, right? Okay. And so if we look at these enzyme activities, what we can see here is 45% of the enzyme population is like this, 20% of the enzyme population looks something like that, and 35% of the enzyme population looks something like this. So this is the total percentage of the total enzymes, and this would be your enzyme activity for these right here. So if we look at this percentage of total enzymes again, this would be your enzyme activity, and we see that they have different enzyme activities for these different colorings. Okay? And so we are going to modify our enzyme activity depending on which of these is going to be the most expressed at that given set of conditions. Okay? That could be the specific pH in the womb. That could be temperature. That could be many things. Temperature being the biggest one. Okay? They're isozymes. They're different forms of the same enzyme. Yeah. So they're all tyrosinase, but they're different forms of it. Okay, so because individual enzyme molecules have stochastically, the time between consecutive reaction events appears to be vary randomly. So remember that when you're looking at an enzyme, it has to reset, it has to have an unbinding, a binding happen, it also has to have diffusion occur, right? None of these processes are perfectly going to be scheduled, okay? They're all going to be basically Gaussian distributions, right? Does that make sense? You're going to have some that happen really fast, some that happen really slow, and then sort of a normal speed that will happen most of the time, okay? And so each of these are going to have some variance. If you get extreme cases that overlap, you can have very long periods of time where the enzyme would have no activity and doesn't do anything. It doesn't bind, it doesn't get anything coming near it, it doesn't release the damn product after it does that. And so these enzyme times can actually be extremely variable. And you're actually seeing that right here. Can everybody see that okay? Okay. If you look very closely, you'll actually see that if you can get sort of an average, and that average is the most common one. Okay? But again, you have a distribution of times. And they can vary quite a bit. The anticipated relationship between the average time increments at different substrate concentrations would be 1 over the time increment average, the average time increment that you would get from that, equals K2 times the substrate over the substrate plus the Km. Okay? All right. Another way of thinking of this is the better it binds to stuff and the more substrate there is to do stuff, the more likely you are to have fast turnover, right? Which is why these terms are in the bottom here. This term right here being the reaction going to product, the more likely you're going to have fast turnover again, right? This, by the way, would be a Hertz cycles, like rotations per minute in your car, right? RPMs. How many times this happens on the average increment, how many times per second. So if we take the output of this equation, this actually reveals the same saturation behavior for reaction rates that we actually observed for the ensemble studies of enzymes. We have that same sort of relationship with our concentration as we looked at before, right? So this is actually the beta galactidase, reaction. It's going to take galactose, and it's going to react it with water, and it will then form this galactose right here. Okay, so upon reaction with the beta galactosidase, I keep jumping to the damn substrate. The substrate, which is GR, this is the GR substrate, is going to produce something that's highly fluorescent, which is this right here. You may remember, and you're kind of getting more into it in this semester, of highly conjugated rings can have a great deal of fluorescence, right? And we can change the absorption of light depending on how much conjugation there is. This has a lot of conjugation, okay? And so it's highly fluorescent. And so we can monitor this very, very well. So this is actually a Lineweaver-Burke plot for a single molecule data. This compares favorably to those from ensemble studies where we would take multiple things together. And so we didn't have to monitor multiple molecules and have the additional error from that. We could just measure our fluorescent species and how quickly it builds up, right? Because it's a nice one-to-one relationship every single time we react. And this actually gives wonderful proof for a Lineweaver-Burke plot, right? Look at how well that fits. Great fit, right? Okay, so again, this shows heterogeneity at the molecular level. This is the log 10 with the number of events. Remember, log 10, so we can actually see this on one plot and it makes any damn sense. But every single unit of change here on this axis would be 10 times the number of events, right? Okay, so this then is the time interval. And so what we see here is, again, if we put more substrate in, what would you expect this speed of this reaction to be like? Shorter time intervals, right? We'd expect more events per time interval. And that's what we see. And we see a pretty clearly logarithmic relationship, right? Okay. What else do we see about this? As we change these, we look at this one right here, okay, which has 10 times the amount of substrate. What do we notice about these number of events? We start getting more and more variability as we start thinning out our concentration. And that's because we can have things like, we need this molecule to hit the damn enzyme, and it keeps popping over here instead with the diffusion instead of going to the enzyme. It's just random chance, right? Okay. Okay, so let's talk a bit about inhibitors. So again, we can inhibit enzymes with using specific molecules. We would typically call that inhibitors. We have irreversible enzyme inhibitors. These are going to combine covalently to the enzyme. They do not dissociate at any appreciable rate. And so they're typically going to be, for our intents and purposes, stuck to the enzyme, and you can't reverse them. Okay? Now, like all other covalent bonds break and reform over time, right? But not at an appreciable rate we're going to wait for. The reversible inhibition is going to be characterized by dissociation of the enzyme and inhibitor complex. This is typically going to be formed with non-covalent interactions because it'll be hydrogen bonding, salt bridges, dispersion forces, right? Things that will easily break and reform at our physiological temperatures, okay? And so we get release of the inhibitor and we undo the inhibition, right? These, they bind covalently, so at room temperature or physiological temperatures, we are not typically going to see a release, okay? It is indeed, and that's why it's irreversible. Okay. These are three common types of reversible inhibition. Remember, these are all reversible ones. They're going to involve binding of our inhibitor to our enzyme. There's competitive inhibition. The naming of these are exactly what you think, by the way. So do not get confused that, oh, this has to be difficult. Okay? So we have competitive inhibition. If you were just to name that off the top of your head, what do you think it does? Competes with? The substrate, exactly. Yeah. So it's going to bind the same place the substrate would bind, right? That's the only way it can compete with it. So if the substrate binds there, the inhibitor can't get in, right? If the inhibitor binds to the active site, the substrate can't get in, can it? Okay. Then there's uncompetitive inhibition. This is going to have an inhibitor that binds only to the enzyme substrate complex. So think of this. It is uncompetitive, right? So it's not just not competitive and not competing for it. It's so far away from being competitive that it's uncompetitive. Okay? And so uncompetitive, you're going to have the substrate bind first, then your uncompetitive inhibitor will bind to another site. Usually it's associated with the active site. Okay, something that would be formed by that binding of that active site. And then it will stick there. Now keep in mind that because the uncompetitive inhibitor binds to the substrate enzyme complex, it actually traps that substrate in there, doesn't it? Okay. Now, this is the non-competitive inhibitor. So what's going to happen is the inhibitor will either bind the enzyme or enzyme substrate complex. It doesn't care. Okay? This typically does not happen at the active site. This usually happens at an allosteric site. And so it doesn't care. If it's the enzyme alone, the inhibitor will bind it. And then it can still bind the substrate, it just can't go forward with the reaction. Okay? If it binds the substrate, the inhibitor doesn't care. It's going to bind. And then your enzyme gets deactivated and can no longer do the reaction. Okay? And this is a nice picture. See how it like hollowed out the reactive part of it? So a pure non-competitive inhibitor, this can bind equally well to the enzyme with or without substrate bound. This is what's considered the pure non-competitive inhibitor. This is the most pure behavior of it. Only the turnover number is decreased, only going to product. The mixed non-competitive inhibitors are going to exhibit some non-pure behavior, meaning that they'll bind preferentially to one of the forms. So a mixed one will bind preferentially to either the free enzyme or the enzyme substrate complex, one of the two. This is just mixed behavior, right? So again, the substrate binding and turnover numbers will both be affected, okay? So you're going to get different binding behavior and different turnover making product behavior. Okay, so this is actually PABA. This is p-aminobenzoic acid. This is a metabolite that's needed by bacteria for synthesis of the coenzyme folic acid. And here we see that right here, PABA. Sulfonamide is an antibiotic. This mimics PABA. See how close it is to PABA? Okay. So what's going to happen here is this is going to bind the enzyme that would normally metabolize the PABA and effectively inhibit it. This will prevent folic acid synthesis. Humans get their folic acid from their diet rather than synthesizing it ourselves. So we don't really care, right? Sure, give us sulfonamide. I don't care. I'm just going to get it from something else. But for bacteria, this is usually a major deal because they are going to synthesize their own. Okay? They do not typically get their folic acid from their diet, at least not the majority of it. Again, the dissociation constant for the competitive inhibitor is going to be given by this same sort of relationship. Notice it is very, very similar to what a Km expression would look like, right? It's just now instead of being substrate, it is the inhibitor, and so it is Ki. Okay? The smaller the Ki, the more potent the inhibition. Again, the smaller the Ki, the more it binds, right? Ki's are much more similar to a dissociation constant. Not quite the same thing, but much more similar. Okay? The competitive inhibition can be overcome by, of course, sufficiently high substrate concentrations. Think of it like this, okay? You're all trying to get out the door, or you're trying to buy, what would you guys line up for and try to buy? All rush to buy. Is there anything you try to buy? Ticket? None of you buy tickets to concerts? Okay. Okay, Taylor Swift is doing a concert, right? Yeah, but you're still queuing. Yeah. You need like a really fast internet connection, right? Okay, so you're trying to get into with a group and see a concert for somebody that nobody cares about. Okay? How likely are you to get that ticket? If nobody else cares about it, you're getting the ticket, right? Okay. Taylor Swift is playing a concert. How likely are you going to get the ticket? No, you're screwed, right? She sells out like, she has like butts purchasing tickets at nanoseconds using supercomputers. It's stupid. But yeah, I don't personally like Taylor Swift, so no, I'm definitely not Swiftie. She's my generation is the fucked up part. Jeez, people. Let her die. Anyways, whole another thing. So if you have enough substrate in this case, you'll outcompete the inhibitor, and you can completely overwhelm your inhibitor, right? But you have to have much, much more substrate than an inhibitor. And this is actually what we're seeing right here. See the curve right here? So with the no inhibitor, we were approaching the Vmax up here, weren't we? Okay? Now keep in mind that 100 in these is the Vmax, because this is relative rate, right? It's the rate relative to what it could be, with 100 being the max, right? Okay, now, so when we have inhibitor in here, what you can see is as we add more substrate to this, we're going to overwhelm that inhibitor, won't we? Okay, and that's because it is a competitive inhibitor, right? All right. Now, notice if we increase the amount of inhibitor, then we can start bringing back that competition, can't we? Okay? This is what this looks like for the binding, by the way. Remember that the competitive inhibitor has to get to the enzyme first to form the inhibitor complex. It will then fall back apart, giving you the free enzyme, which can then bind the substrate, right? Okay, I'm going to take a 2-minute break and use the restroom.